population development. We also can relate it to different government response events, as well as identify key dates.
Hello, depending on when you're dialing in from, good morning, good afternoon, good evening. I was just reflecting this morning on the fact that this is my 10th year attending VIS, and I really wasn't expecting to be attending it from my couch, but so goes 2020. So welcome to the MLUI 2020 workshop. This is machine learning from user interactions for visualization and analytics. And I want to start off just by thanking the whole organizational team who also are coming together from across 5 different time zones. All of these organizers are going to be helping us to facilitate some of the discussion groups that we have built into our sessions today, but a little bit more on that in a bit. For now, my name is Wenskovitch. I am chairing / moderating this first session. And then for the second session that's coming up in 2 hours, it'll be Michelle Dowling who is covering that session. So I just wanted to start off with a quick bit of introduction to the workshop because, well, this is a nice virtual workshop. You might not have been attending VIS before, and so you might be a little bit curious about what our goals are, what it is that we're really trying to do here. So our idea behind this workshop is request to unmute. So hopefully you were able to hear me, but maybe you weren't able to hear me. So starting again with the workshop introduction. Okay, we were looking a little bit beyond the explainable AI research agenda, which is going from the machine learning to the visualization to the user. We're also thinking a little bit beyond human in the loop, which is we're going to fiddle with some knobs and dials as the user to tweak the machine learning. What we're really thinking about is the user interacting directly with the visualization, and from there going into the machine learning algorithms to personalize the visualization to make the visualization a bit better overall. At the high level, our workshop goals, well, we're trying to envision what all we can learn from the user. We want to try to be cutting edge. We want to try to speculate about what could be done now and what could be done in the future, and what new visualization capabilities could result. We were thinking about a research direction, trying to figure out what new research is needed to achieve this vision of what VIS capabilities can we produce. And we're also looking toward building a community of interest from across all of VIS. So just a quick overview of what's going on with the program. So I'm giving the introduction and welcome right now. And then our first keynote, speaking about machine learning meeting visualization, is Michael Settlemyer. We then have a talk from Ming Wang talking about interactive dimensionality reduction and bridging cognitive gaps between users and the models. And then we'll break out into a couple of discussion groups, which the link for that was already posted up into the Discord chat, but we'll post that link again as well when we're starting to move into the discussion. In the second session, we have Alvitta Ottley, who will also be giving a keynote, this one on using models and predictions to help humans and computers click. And then we'll also have a set of quick late-breaking work lightning talks. Then we'll have another discussion session, and we'll wrap up at the very end with some synthesis and next steps for our workshop, presumably a MLUI 2021. So a couple of quick links to point out. I already have both of these up in the chat, but you can get to our website at learningfromusersworkshop.github.io. This contains both the agenda and the fancy information about this year's workshop, but also links to the 2018 and 2019 versions of the workshop, in case you're curious about what we've done in previous years. And then the link to the discussion rooms, which again will happen in both of our sessions today at tinyurl.com/MLUI2020 links. As far as the discussion sessions go, we have 5 different groups that we would be breaking out into, and they're based off of this loop that we created based off of the first year's workshop content, what different categories we want to have discussions about. We're going to change the names of some of these a little bit, where this interactive visualization of machine learning data kind of overlaps with this semantic interaction research, and our capture logs we're extending to also consider provenance. But then we also have personalizing visualizations, the existence of explainable AI as part of this interaction between user and machine learning, and then also evaluating the results as a user who is in the loop. But that's probably enough of hearing from me. I would like to now introduce our first keynote, who is Dr. Michael Settlemyer, introducing the topic of machine learning meets visualization. So Michael is a junior professor at the University of Stuttgart, where he works at the intersection of HCI visualization and data analysis. And his talk is going to talk about machine learning and visualization from both directions, starting off with VIS for machine learning, this idea that visualization can help machine learning researchers and practitioners gain insights into their models, but then also turning it on its head and talking about machine learning for VIS, guiding the visualization designers and the analysts toward interesting patterns in their data. And so that's it for me. We can transition over to Michael, and he can get started on his talk.
Thank you. Let me try to share my screen now. I guess you can see my screen?
Yes, good to go.
Good. Hello, everyone. Welcome also from my side to IEEE VIS 2020. Thank you, John, for the introduction, also for the invitation to give this keynote at this fantastic workshop. Everything is a little bit different this year. We know we're not meeting in Utah, which is a pity, but I think the OC, the organizing committee, did a fantastic job. So I'm looking forward to a great virtual event and also great workshops, of course. So I thought, let's start with like a historic a view of what happened with the two areas, visualization and machine learning, over the last couple of years or even decades. So when I went to undergrad school and to grad school, I was focusing on HCI research, but then I think all around me it became clear that, like, we can store so much data. So I got soaked into this area of visualization, which is kind of super cool, as we all know. And some 10 years ago, then I think it became clear to everyone that we're now seeing something big happening here. There was like the book, The Fourth Paradigm of Science, published, like, advocating that data will substantially change the way how we're doing science, but also will change industry and society altogether. So back then, I just have moved from my position as a PhD student in Munich to a postdoc position at UBC in Canada. I was, like, fully soaked up in visualization. I guess, like, nowadays we would call myself a data enthusiast. That was great. And I think, like, many people also were like that back then. And then I detected sort of this area of machine learning. I heard about before, but like at UBC, there were people like, Kevin Murphy, Kevin Leighton Brown, and Nando de Freitas, really great people doing machine learning stuff. And I was like, this is so great, machine learning. And they have, like, this hardcore algorithmic view, and VIS, they have like this human-centered view. They should be like a nice team to, like, change the future. And then we all know what happened. So this little COVID-like graph here that we're seeing is sort of illustrating that, like, machine learning really got big, and everything changed. We had, like, big data, we had deep learning, we had neural networks doing great things. But for me, always it was sort of strange, because the main focus was really this full automatization without any human in the loop. So everyone is not talking about self-driving cars. It's like, automatically playing Go, artificial intelligence, and writing a Bach song, like, without a human in the loop. And I think many of us in the VIS community were sort of wondering, like, where is actually the human in the loop? And I think, like, now things are changing a little bit again. And I do still believe in my optimistic worldview that, like, the human in the loop will come back, and that not just, like, AI will take over. And I think, like, many of you will share this view. And for that, I still feel like the combination of machine learning and visualization will be at the heart, and machine learning and user interfaces more generally, of, like, these interfaces. So there's, like, different questions that we need to answer. And I think two important ones that I want to focus on today is, like, how can the fields benefit from each other, and also how we can combine knowledge and insights from both. And this is sort of like also the outline for today that John already mentioned before. So in part 1 and 2, I will first talk about VIS for ML, and then ML for VIS, and mostly a report from our own experiences in these areas. And in part 3, I want to do, like, a little bit more forward looking and talk about, like, the holy grail for me, which is, like, VIS and machine learning combined together, and focusing more on, like, the challenges that I do see ahead, and that I hope that like, this workshop also can contribute to. Okay, let's start with the first part, visualization for machine learning. So I think all of us now know that, like, visualization can really play an important role in AI, in machine learning. Interestingly, I think one of the first influential papers came not from the VIS community, but from the ML community, and, like, showing how visualization can actually help understanding these deep neural networks. But I think ever since, there have been, like, many great examples, and I'm sure you guys did also, like, many of those. Just some examples that I personally like is, like, explaining gradient descent, which, like, is a component often used in in machine learning techniques, or explaining TensorFlow, many great interactive visualizations that can help to explain what's going on in these models. So we also have worked on ideas on how to use visualization to support machine learning developers or support machine learning designers and researchers. So I think our focus has been a little bit different, though, which is we're more looking on like a model agnostic way of using visualization. And so the thing that we were looking is like on a dimensional visual parameter space analysis. So for instance, here, like if you're looking for a dimensionality reduction algorithm, which we all know they're great and we want to look for, you need to like sift through a whole lot of like different dimensionality reduction algorithms to find what you're looking for. So just like dimensionality reduction, for those I'm sure like everyone heard, so just like very quickly, what are we talking about? High dimensional data, and then we have these algorithms that help us like project the data into 2 dimensions, and then usually we have some sort of visualization that help us to understand what's going on in the high dimensional data. And then as like a data scientist, your job is to do that, but there's these many algorithms. So we did a field study to try to find out how do people actually use these algorithms, and which algorithms do they use after all. So PCA is like the classical one, which is like a typical thing you would try first, but then you might not be happy on the results. So you try something else like TSNE with a parameter setting, and you're still not happy. Then you try another TSNE with like another parameter setting, and you see like you're getting more and more unhappy. The reason is because like this approach is really trial and error. So it's not systematic, but we probably all did those approaches at some point in our lives. And we're just exploring the space of possibilities, and we don't know when we actually reach a good solution. So what we proposed instead, and that's a general approach, it's this idea of visual parameter space analysis. So instead of just like doing step by step sequentially going through the algorithms, we want to sample them in parallel and then have a visual interface that allows us to look at a large set of these model outputs. So usually we would do that with like a meta map using some dimensionality reduction algorithm, for instance, again, where we can sort these results by similarity. So here's one example where we did that for dimensionality reduction algorithms. Let me briefly walk you through what we're doing here. So like in the center, we're seeing this meta map that I was just talking about. So each single point that you're seeing here is basically for one given data set, a projection, a specific projection. So there's some PCA, and we can see also on the right-hand side, there's like a TSNE. If we click on them, we will like, see the details on demand. So like we created like 1,000 different projections here and used some TSNE algorithm again to map them. And then we also, on the left-hand side, we see like the input parameters, which we color code. So we know, for instance, TSNE, this dimensionality reduction algorithm, has 2 parameters. There's the perplexity, and there's this epsilon, which we map in this 2-dimensional color space here. So I hope you can see the video. So now you can see like, I click on a point, the screen point is MDS. And the cool thing now is we can do like, many cool things. So now we do linking and brushing. And with this systematic visual parameter space approach, we can learn some interesting things here. So like what I'm doing, I'm hovering over. Let me stop the video here for a moment. What we're seeing is the highlighting in the parameter space on the left-hand side shows that like all these plots, these projections that we're seeing here in this local neighborhood, that means those are similar projections. They have very similar perplexity values, but they seem to have epsilon values all over the place. This is somewhat interesting. So we also can like, look at that from the other way. So now we select actually projections that have the same perplexity value, and we see there's a nice a smooth transition here of like, similar graphs. If we do the same for the epsilon, it's all over the place. So we can learn something about the sensitivity of these parameters in that example, seeing that perplexity actually has a nice behavior in terms of sensitivity, but epsilon has not. So as I said, so this visual parameter space analysis framework is really a general idea that you can use for all sorts of input-output models. And in fact, so if we look at the literature, people have used it for a long time, but classically more on simulation models, like classical ways of modeling. So we also did that, for instance, for image segmentation, like you can see here, brain segmentation algorithms. What you see right next to it is like a one-dimensional over time bird flocking simulation. So these are simulation models that we sampled and then use a visual parameter space analysis approach to look at them. But it turns out, and I would argue it's also a very well-suited approach for looking at different machine learning models. So I just illustrated that with dimensionality reduction. Why? Because I love dimensionality reduction. We have done so many things, but we also used it for other techniques. So clustering is again like an input-output model that we can sample, and then you can learn when should I use dbScan, when should I use K, which how should I put the K and that sort of stuff. We also at AVI this year we had a paper where we used it for classification models, and you can also use similar ideas for active learning models, of course. So this was part one, and now I want to go over to part two, where I want to talk a little bit more about the other side, which is machine learning for visualization. So here's our little COVID-looking overview graph again, which I think shows an interesting thing here, which I feel like when I observe the world and look at these other areas, which are illustrated with the gray points here, I think most of the other areas they're taking machine learning techniques and try to apply them to their own field. Here in visualization, like for the last 5 years, I had the impression that we're mostly looking at like the other way around. So we were mostly looking at visualization for machine learning. This is, of course, like a very nice thing to do, and machine learning people might be happy about it. But I think like it's similarly important also for the VIS community to look at how machine learning approaches can be leveraged in visualization. And this is what we want to do now. And I think this is also, I want to spend a little bit more time talking on that, because from the webpage of MLUI, I got then this should be the focus here. So rather than focusing on what visualization can do to support machine learning, this is what we just talked about, the workshop seeks to contribute on how machine learning can support visualization. So this is exactly this topic of part two. Okay, so the motivation for me in that area is really like one of the VIS grand challenges, or say let's info-VIS grand challenges, which is designing good abstract data representation. So we all know this problem. So we have some tabular data, like in this case, and then we want to visually encode that. You of course know how to do that, but there's like many people out there that just go to Excel and then they would get something like that. And we all know 3D bar charts, of course, are the most fantastic visual encoding that we have, because we can clearly see the pattern. Okay, so this is now where interactivity would help. But I would like to ask you who sees the pattern? And I think very few people actually do. If we decided to visually encode that data differently here with a heat map, we immediately see that there's an interesting pattern, the question mark here in the data. So the question is now, how do we get to a good visualization starting from the data? Okay, so the classical approach, I would argue, is really, we're running some user studies and then we provide guidelines. So here's one of my all-time favorite user studies from Goniam and Jean-Daniel Fekete, comparing matrix-based visualizations with node link diagrams. And then we could, based on their results, derive some guidelines saying that matrix visualizations are actually not that bad. They're still not heavily used, but look at that paper and learn about the reasons why we should use them more often. However, there's an issue with guidelines. Guidelines are rules of thumb. So like this is nothing we can actually put into an algorithm and an optimization algorithm to automatically get good results. And so this is something that for me like started 10, 15 years ago, where people started thinking more deeply about quality measures. And here I would call them mostly heuristic-based measures, where you say like, there's a certain thing I want to see in the data that I can formally express and put into an algorithm. So an example that I like very much is like this paper by Mike Sips, where they proposed these metrics for scatter plots and for formally describing what makes classes separable. So class separability measures. And one measure that they proposed is simply called the Centroid Measure. They had a more complicated name. I just call it Centroid Measure because like it goes to the heart of what they're doing. So you compute the centroid for each of these classes, and then you basically iterate through all of the points. So, and for each point, you check like which is the closest centroid. So here we have a blue point and a blue centroid. So the closest centroid is a blue centroid. So this is something good. So the value of the metric would go up. But here the red point is actually closer to the blue centroid. So this is something bad, and the value of the metric would go down. So this is pretty cool, and we can like, do great things like, selecting interesting views in large scatterplot matrices, for instance. So this is also what we thought, and we went ahead and used these metrics for our own data. But then we found out there's sort of like low generalizability across data sets. So what does this mean? That basically means when we used it on our data sets, these metrics did not really perform well. So then we actually set out and we tried it on 816 different scatterplot data sets, and we found there is some sort of failure cases in almost 50% of the cases. And if we excluded the synthetic data sets and only looked at the real data sets, we found that almost in 70% of the cases, there was something going wrong with these metrics. So this was the time, like 2013, when I started talking to Michael Oppetit. Like he's coming from machine learning, and he proposed, hey, this is essentially a machine learning problem that we're looking here, or a computer vision problem. So forgive me my very naive view on computer vision, but like for me, computer vision is a very simple problem. So we have like, cats and dogs, and we like, feed many images into a learning environment. And then the idea is that we get an algorithm that gets like a picture of an animal unseen, and then like you automatically can say whether this is a cat or a dog. So essentially, this is also the same problem that we're seeing here. So we have like a scatter plot with separable classes and one with not separable classes. And then we would like to get an algorithm that for an unseen scatter plot says whether this is separable or not. So this is was the idea, and we actually went ahead and did like, an easy implementation using some binary classification model. So what we did is basically in the first step, we gathered some human ground truth data, annotating like whether something is separable or not. And then we predicted that with different measures. So like this is the classical model selection step in machine learning. And then we can evaluate the quality of each of these models by looking at classical evaluation approaches in machine learning. So like the binary classification area under the curve bootstrap, which we did here. So like here we've like feed in these like, 30 something models that we found in the literature. And then we can actually say like, how well are they doing in terms of predicting the human judgment? So this is what we're seeing here. So it's really a binary classification problem, simplified, either like, separable or not separable. So that means like if we're seeing 50% here, that's just a random guess. If we had 100%, we would have like a perfect prediction of the human perception of these patterns. So, and then we actually ran that through, and interestingly, the Centroid measure by Mike Sips and colleagues won with like an average AUC of 82.5%. So there's some things to explain here because like, you probably noticed before I said, oh, there's many problems. So we oversimplified the problem. We're only looking at clear cases here. We're just excluded all the complicated cases in the middle. This is something we're still working on. But also to be noticed, of course, there's still 20% room for improvement. And that's what we actually did in a follow-up paper the year after, where we created 2002 measures through a systematic search. So systematic search means like we tried out different proximity graphs, and we also tried out like different purity functions, and we combined that. So this is lots of mathematics and fun. So we had like Delaunay graphs, KN and G graphs, all sort of that stuff. And the cool thing is now we could automatically evaluate those based on how humans would perceive them. And so the results showed that like 58% of our 2002 measures performed better than the best state-of-the-art Centroid measure. And the best measure that we got even got up to like an AUC, average AUC curve of like almost 93%. So this was quite cool. So now, of course, like many people would ask, so why are we doing that? And I think like, you know, there's many practical things that we can do with these sorts of measures. Of course, like first, let me note, why are we using scatter plots? Of course, scatter plots are an important visual encoding, but they're also like the fruit fly of visualization research, to quote Ron Rensing here. So they're complicated enough so that we can learn something interesting, but they're still simple enough so we can learn about the fundamentals of visualization. But here, the practical things is like, you know, if you go to like, you know, high dimensional data, you're selecting views in a 5-dimensional scatter plot matrix. That's not a big deal. If we go up to 200 dimensions, of course, like we have 20,000 views, and an algorithm like that would be like really helpful, a measure like that. We also plugged it in into a linear dimensionality reduction framework, so like an LDA, PCA sort of thing, where we now can use these metrics, these measures, as optimization criteria. And we did actually a comparative study, and we showed that our method that we created with these measures even outperformed the classical LDA approach here, linear discriminant analysis. Of course, there's also other tasks. So we did that for non-color coded scatter plots. So this would be the classical idea of modeling clumpiness, or also like, you know, classical clustering approaches would do that for you. And so like, again, we fed that with like, you know, perceptual data. We do some perceptual modeling pipeline using machine learning techniques here. And then we created this technique called ClustMe, which seemed to perform rather well also compared to existing approaches. We did that also for color coding. So the idea is here to have an algorithm that automatically assigns colors in a way to classes in a scatter plot that makes them for a human easier to differentiate. So in here on the left-hand side, we see like, you know, plots that were low ranked by our algorithm. And on the right-hand side, we see scatter plots, so color assignments to scatter plots that were highly ranked with our algorithm based on that approach. And of course, there's also other visual encoding. So here's like a thing that we will present this year. It's a collaboration with Yunhai Wang, where we use this approach to sort like, you know, the different streams in a stream graph. And so like, you know, on the left and in the middle, you see existing techniques, and on the right, you see our technique where we resorted that. Okay, so why do I think this is so important? I think there's a few things to be noted. I think like, you know, there's two general streams that make a lot of things possible that have not been possible before. So one is like scalable data becomes really available now. So there has been, for instance, the VISnet paper at CHI 2019, but there are other papers that just like offer a lot of data sets that we can use for such approaches, such learning-based approaches. And at the same time, we also get into more scalable methods. And with methods, I mean both. On the one hand, we get more scalable methods to gather human subject data, like mechanical Turk studies. And on the other hand, I think like there's this great machine learning, deep learning hype. Well, the word might be negative, but this essentially means for us, there's like new models every month or even every week that we could try on these sort of approaches. So eventually it might even lead to a new paradigm, although I know that's a very heavy word, but I think it's a really interesting idea that we could try and hope to systematize the visualization, formalize the visualization research a little bit more. Of course, so far we're mostly focusing on perceptual modeling of static visualizations. Including interaction is much harder, and this is like, what I would like you guys to do. It's a fantastic topic, and I think like it's at the heart of the MLUI workshop here. And I think similar ideas could be tried out, of course, for like interactive visualization. But as we know, interaction makes things, of course, harder because like, humans are getting closer into the loop. So this was part 2. Now we get to the last part 3, visualization and machine learning. So for me, I think the holy grail is really if we can combine those two approaches into something that is helpful for users that are not machine learning developers and that are not visualization developers. There's many people out there that like could benefit from a neat combination, like a close combination of those two areas and the ideas that we're doing there. I think there's many great quotes that we can use here. So this is just one that I saw Jeff using just a month before the lockdown and the pandemic hit the world. Like he gave a talk in Stuttgart and he used this quote by Michael Jordan, not the basketball player, but the famous statistics professor at UC Berkeley, who says like, we need well thought out interactions of humans and computers to solve our most pressing problems. And I think this is what I believe, and I guess this is also what many of us believe in this community, that we need to get it. And this is not necessarily something new. So like in my own PhD thesis, for instance, like this car example that we're seeing here, we combined algorithmic approaches with human in the loop visualization approaches. And those turned out to be the most successful approaches. But also more recently with Manuela Waldner, where we, like in a sort of semantic interaction type of tool, let journalists organize their content and then like, provide like recommendations of what else they can look at. So there's many challenges ahead. I want to talk about 3 of these challenges that I see, and maybe like they can be also helpful for this community, for this workshop to think about. So first, solving real problems. Yes, this is not new. So I think solving real problems is really something that we have talked in the visualization community quite heavily. Myself also, like, with Mariah Meyer and Tamara Mansa, we had this design studies paper that we were super proud of. And I think like it helped some people, at least it helped us, like when we are working together with like real users on real problem. And I think this is helpful, but I think for the, like, the combination, the close combination of machine learning and visualization, we need to go further. So what do I mean? So I think like there's different types of design study methodology. So this paper that we wrote back then is not meant as the one and only way of doing design studies. So Michael Oppermann, for instance, he will have a great paper at the Belief workshop today where they think about data first design studies. So instead of like, starting with like reaching out to users, they start with data, which is, I think, like a great idea. In machine learning, we probably also need to start with model-first design studies. This is an approach that I'm seeing, of course, at VIS, for instance, very often, where people start with simulation models and then look at like, how visualization can help to transport insights to users. In the end, I think like, the original idea of problem-first design studies is still important, but I think there are some specialties of like this ML plus UI, which make them different from what we had in mind originally. And I think like what I often now use as a way to describe my work is like, I say we're working on human data interaction or human model interaction. It's about the interaction between the humans and the data. So visualization is one way, but there is like, many other ways and many other interesting problems that we need to focus on. It's a little bit broader, I'd say, than visualization. But I think at the same time, there's like, this idea of it can be much broader in terms of like supporting the tasks that are out there. So here's one paper that I think is really, really great, and that was very influential for me by Salima Amershi and colleagues, which was called Regroup, where they basically on Facebook allowed users to select groups of people and then would automatically, in an active learning sort of fashion, like, having a computer suggest, recommend other people to also invite to your party. We know this is tricky at pandemic times, but like, that was the idea. And I thought this was pretty cool. We also did something similar where we had like data from songs, music songs, and then like you would listen, and while you're listening, you can actually look at the tags of these songs and select tags. And with those tags, you get actually recommendations for the next songs, which allows you to like, get out of like, the classical recommendation black hole loop where you always get the same. So the thing is, if you submit those works to VIS, you will most likely get like a very critical VIS review saying, oh, there's no new visualization. It's very like, HCI-ish. And you see those papers are not published at VIS. So at VIS, I feel like we're still looking at these like, super complex interfaces, Photoshop-like, while the rest of the world already has moved on to like having something complex like apps as, something compact, not complex, like apps that focus on a specific task, but do that very, very well and are very good in terms of usability. So maybe we also should be more open towards that. Okay, so with that in mind, human data interaction puts interaction, of course, at the very center of what we're talking about here. So, and then the typical question I'd like to ask is linking and brushing really all we have to offer? And I think no, there's great things like Alexander, he's also on that call today. And like, they did stuff on semantic interaction, which I love. There's also Remco Cheng, IPCA, great stuff where you interact with like these visualizations with direct manipulation. And then by doing that can change the model behind it. There's other things, there's interactive learning. So we have done stuff along those lines where you actually, you interact, and by the way you're interacting, you also have other ways of updating the model in the back. I would also argue we're still not doing enough post-WIM stuff. There's now like, stuff like immersive analytics going on, which is great. I think the most promising parts of that is really about the interaction method. So here's a great example that unfortunately never got like, widespread in the VIS community, but like it's this idea of using a mixing board to interact with high dimensional spaces, which I thought was a pretty neat idea from like, already 13 years ago now. So with the interaction as the first class citizen now, we need to, of course, think about human in the loop. So interaction means there is a human interacting with something. So in other words, there needs to be this human in the loop. And the question that I always ask myself is, when do we actually need a human in the loop? Then it's like more a VIS problem, or when can we do full automation, which then would be just a classical machine learning problem. So again, so a few years ago, we came up with this model that like for classical analytical tasks, I feel it's still helpful. So it has these two axes. One is the task clarity, and the other one is the information. In other words, now, if I have like a crisp task, I know exactly what I'm doing, and I have like enough information to model that, then I don't need a human in the loop. Self-driving cars, like I have like, very clear task I want to get from A to B, and we're getting there. We're getting enough data to make that fully automatic. But there's many, many other problems. For instance, like, writing a Bach song, that's probably boring, but you want to have like, a composing system that has a human in the loop and has an algorithm in the back that can support him, or many different algorithms. That's the sort of idea. And I think like we're doing great. So we're sampling that space, but we need to get even better. So it's just samples. And usually what happens in the typical visualization project is we're making things clearer. So we're moving stuff towards the full optimization. And so this is somewhat depressing, because like in the end, like, this red part is getting bigger and we're getting like smaller. It's not true as that. So there was a paper by Joe Wood and Jason Dykes where they argue, no, with every design study that we're doing, we're also like, moving arrows in the other direction. So we identify new problems. But still, I think like what we need is really a more holistic understanding. We need a theory, we need a science of interaction. Again, this is nothing new. People have argued for that a long time ago, but I think it's more important even nowadays. So challenge number 3 is scaling up things. So there is an observation that I'm sure you guys also already made. So the typical machine learning data size in a machine learning paper, at least from like, the sample that I'm seeing here, is usually much bigger than like, the data set sizes that we're using in our visualization papers. Maybe not in VIS, but like definitely in InfoVis and maybe also in VAST. Interestingly enough, I would argue that like from the time requirements, it's the other way around. So in machine learning, what you do is you let you run your model overnight, and then the next morning you show up and you look at the results. In visualization, we want to have ideally interactive frameworks, or at least we want to have analytical rates. So in a few seconds, we want to get some feedback to the user. I think there is some promising trends. So LDAF is just going on in parallel. Kudos. I think like we need more like that. But also something that I've been personally interested for the last couple of years is like what we call progressive analytics. So the idea is like progressive JPEG. Instead of traditionally like building up things step by step and then showing a picture, you would increase the granularity of the picture. And then you can start working on this data right away. So there was a great Darkstool seminar we had on that topic, and I see also first papers coming out, like Nicola Pizzotti's paper on progressive TSNE, which I think is really fantastic. You should go and read and use that. Of course, there's many other challenges. So things that I did not talk about is like the design process. Whenever I see that picture, you've seen it before, the modern data scientist seems to be like this wonder person that can do everything. I think like in the HCI and the VIS community, we have a healthy discussion on collaborative approaches, on user-centered design approaches with different roles. Evaluation, things change. How do we show that there's something useful? There's again something going on in parallel. The Belief workshop last year, there was a workshop, Eviva ML, people that think about those problems, and of course many more. Okay, so with that, I want to conclude my talk with a quick summary. So we started out talking about visualization for machine learning. I told you a little bit what we're doing with visual parameter space analysis and illustrated that with dimensionality reduction. Then we talked about machine learning for visualization, and like here, the provocative idea of automatizing visualization design. After all, it's probably gonna be semi-automatic, but you get the idea. And then in the final part, we talked about combining visualization and machine learning, and at least the challenges that I do see ahead of us to tackle. So what about the future? I think it's not that bad. I think things are changing. And if I want to be optimistic, I think that's going to be the next big thing. People also think about human-centered data science. Now, this is something like when I mentioned that to machine learning people 5 years ago, they stared at me with disbelief. Now, this is a thing, explainable AI, trust in AI. And also this workshop, I think, is at the very heart of this movement. So why is this so important? I think like if we look further back into the past, like we had like things like the telescope, the microscope, they fundamentally changed the way how we see the world. I think this is what we're doing today, but I think it needs to be a combination of approaches in machine learning, UI, visualization. On that note, I want to say thank you to my team, to the many, many collaborators, and of course to you guys for listening. I'm not sure how many people were there. I only can see my screen here at home. It's pandemic. We hope it's over soon, but thank you for your attention. Now I'm happy to take any questions if that's possible.
Great, thanks a lot, Michael. That was a really fantastic talk. So if you have any questions for Michael, we do have a couple minutes to spare for questions. Can you post them into the chat either in YouTube or in Discord? We actually don't have any questions yet, so I guess your talk was already really comprehensive and addressed everybody's questions. I guess one question that I can think of I guess one question I can think of to start off with is something that you touched on at the very end about evaluation. So you were discussing the idea of having human and model problems, driving the idea of developing visualizations by considering the model first. And I'm curious how you would go about evaluating systems like that. How can you judge that the user is really understanding the model and using the model accurately?
Okay, so this is a very good question. So I think it really depends on which type of system you're building. I think like with some systems, you can use classical metrics like time and error. When like you go, for instance, like, say like this example of like, putting together a group that you want to invite to your party at home. I think like, here you can say like, okay, this is just going to be faster. But then of course, the hard thing is like, if we talk data analytics here, and I think like, we need to start where we already started with visualization approaches. We need to have like really a good and in-depth qualitative analysis of that. So you could do like things like insight-based studies, which you, I think, also did, or at least like, people in your group did. You can like, do like MLUIs, like multi-dimensional in-depth long-term case studies, design studies, those sort of things. I think this is needed to first get a grasp on like, what are the metrics that we want to optimize for. I think this is needed if we really go for complex. And like, if this is something for the audience that like is of interest to you, of course, like you should stay in that workshop. But Believe is a full day workshop, which is just going on. And I think there should be like, some discussions about that as well.
Great. And I guess just emphasizing the fact that you should attend Believe in the afternoon sessions, but stay here for MLUI at least for the first 2 sessions of the day.
Yes.
So
here it's already afternoon, but
so there's plenty of applause for you up in the chat, but no specific questions up until this very last one that just came in from another Michael, asking for maybe just a comment or a question in the direction of tasks, things about visual quality metrics that are effective only for certain tasks, like clustering and outliers, but that the task can change in your exploratory data analysis process. Do you have any thoughts about this idea of task changing over time and how to support that?
Yes. Hi, Michael. Thanks for that question. Of course, that's also a great question. So we're starting bottom up here. So there's different approaches, and other people are also doing that. I think there was the Draco paper, for instance, that like, took a more holistic approach on that. I think like we need to think about the capabilities of modeling perception of different tasks. And then the next step, of course, will be to combine it into an analytical framework. So for us, like, or at least for myself, I often go back to perception because this is something we can gather like, human subject data on that is sort of like, can serve as ground truths. If you go into the cognitive bits and pieces, the analytical bits and pieces, things are becoming much harder. But I think like, coming back to this last challenge that I lined out, if we're talking about really large data sets, we need those metrics. We need to understand how people perceive certain data sets. And we can do many good things, like we can use the perceptual measures that we're working on and compare them with data space measures. So measures that work in the high dimensional space, and compare things like, I see clusters in the low dimensional space. Are those also clusters in the high dimensional space, and that sort of stuff? I think much more of these metrics as guidance. And that's why I like, I joked about like the full automatization of the VIS design process, which I think like, it's too much of a wicked problem here, but it can help us. And it specifically can help users, guide users towards interesting things, and also warn them about potential false positives that they might be seeing.
Great, thanks. Yeah, that definitely is a lot to think about, both from your answers and from your talk overall. So we do need to move on to keep on to our workshop schedule. So thank you again, Michael, for the keynote presentation. That was really fantastic. The next talk that's coming up is from Ming Wang, who is going to be talking about bridging cognitive divides between human and model in interactive dimensionality reduction. I apologize just quickly if we didn't get to your question for Michael. If you want to put it up in the chat still, I'm sure Michael can get around to it eventually. But Ming, take it away.
Yeah, thank you, John. Yeah, first let me share my screen. Yeah, sorry about that.
So while you're fixing that, let's go to one more question for Michael. So Michael, there's a question about, do you have any comment to people from the fully ML community about how to deal with missing data from a visualization perspective?
Okay, so I was just looking through the Discord. So the question is recommendations for ML people, how to look for missing data.
Right. Any comment to people from fully ML about how to deal with missing data in that VIS perspective?
Yes, so that's so this is nothing I specifically focus on in my work. It's of course like a very important task. I think like you can of course use something like, you know, a perceptual modeling task or a perceptual model here as well, which would be more like an outlier detection model, and people are working on that. So like, you know, spotting things that look different, look strange. So of course, like, you know, Jeff Hare, Trifactor, they're heavily working on that. Like it's a human in the loop process. And I think like connecting that to one of the other questions here, you actually do have a nice metric of success, which is basically if you just take 4 hours instead of a week for cleaning your data, and then that would be something really good. I think like, you know, it's gonna be like one of these machine learning and visualization systems. And for like, you know, more detailed replies and how to exactly do that, I would actually reach out to Jeff Hare, for instance. Yeah.
Okay, great, thanks. So to the technician in the room, can we give Ming back the co-host permission so that she has the ability to share her screen? Okay, Ming, I think you're co-host now, so see if you can share your screen now.
Yeah, I will try again. Awesome. Can
Okay,
you see my
perfect.
screen?
Yes, good to go. Thanks.
Awesome. Yeah. Okay, awesome. Yeah, thank you, everyone. And thank you, John, for the introduction. And I'm Ming, and I obtained my master's degree from Dr. Norris Group. So today in this presentation, I will talk about our work on bridging the cognitive gaps between user and model. So our lab has previously developed a great tool called Andromeda, which relies on the WMDS. It allows users to shift emphasis to different dimensions so that they can explore data from different aspects. And a lot of great work has been done to enable these pipelines to embed 3 levels of interactions: the surface level interaction, parametric interaction, and observation level interaction. However, we noticed some gaps between our Andromeda system and users. So in this work, we are trying to study these cognitive gaps and propose and evaluate our solutions. So the cognitive gaps are caused by 2 black boxes problem. The first black box is the underlying algorithm. The algorithm, the underlying algorithm of the machine learning-based interactive visual analytic system. So although the underlying algorithm can process the data and provide a useful result, it does not provide any justification or rationale for its output. So this makes it difficult for users to decide whether they should accept the result or not. And here we recognize 2 cognitive gaps. The first one is the highlighting relevant data points. And the second one is the understanding the WMDS dimensions. And the second black box is the human cognition. So user would conduct series of thought process before interacting with visual analytics system. And their interaction will influence the results generated by the underlying algorithm. Unfortunately, the human mind is a black box close to the algorithm, and the algorithm may fail to capture user intention, and this led to our third cognitive gap, constructing and deconstructing cluster. So in our work, we identify 3 cognitive gaps in our system, and next I will talk about their details and our solutions. So the first cognitive gaps is users don't know they need to highlight all the relevant data points. So when user try to move the zebra away from giraffe toward the rabbit, they should not only interact with the zebra to change its position, but also highlight the giraffe and the rabbit because they are relevant to user intention. And also our Andromeda model only consider highlight points. So, but some user, however, they only highlight the zebra to change its position, but without highlighting the giraffe and rabbit, which means they don't know they need to highlight all the relevant data points. And this is probably because the mixing of considered and unconsidered point in one visualization. So we propose two solutions. The first one is the foreground and background view, and the second one is distance lines. So this video just briefly show our solution. So once user click a point, the third dimension will be added into the visualization to pop the interactive point onto the foreground and dip and touch the point to the background. And also we add the distance lines between the dragging point and other considered points, telling user that this dragging point is only moved with respect to other foreground point. And also the color of distance lines shows the relative distance change. The yellow means the large relative distance change, where the dark blue means the small relative distance change. So to evaluate our solutions, we conducted a user study with 69 students in an undergrad level data science course, and they have learned the MDS in their class. So we separate them into two groups by seating location. The first group, the treatment group, we gave them the Andromeda version B, which has all the new features. And for the control group, we gave them the Andromeda version A, which only enabled the basic functionalities. Then we asked them to explore same animal data set and answer the same survey questions. So here I just briefly mention the result. So the results just demonstrate that the significant improvement for the version B on highlighting relevant data points, which means our solutions, the foreground background view and the distance line can encourage user to highlight all the relevant data points. Okay, so next is the second cognitive gap. And this gap is, it is always difficult for user to understand the WMDS dimensions. And this can be further separated into three aspects. The first one is after changing the weight of one dimensions, like these two graphs, it will be hard for user to know like how data rotate to generate this new plot. And also, it is not intuitive for them to figure out which side has large data and which side has small data. So, and also it is not easy to see the correlation between multiple dimensions. So currently, our user had to hover on the points one by one to compare their values and to guess the potential correlation between multiple dimensions. And that is not efficient and also not accurate. So our solution is the dimension assist feature. And now user can just hovering on the slider and they can figure out the chimpanzee. The bottom one has the largest active value. So to evaluate our design, we did a pilot study. We asked 8 participants to do this pilot study, and they have different backgrounds, span multiple disciplines. 3 of them learned and used MDS, 3 of them learned but never used MDS, and 2 has never heard MDS. And again, we separate them into two groups, the treatment group and the control group. So the treatment group, they used Andromeda version B, which has the dimension assist feature, where for the control group version A, they do not have the dimension assist feature. Yeah, so Then we asked them to answer 10 related questions and did a follow-up interview so that we can get more insights. And from the follow-up interview, the participant mentioned that the dimension assist feature is very useful for finding the extreme and describing dimension correlation. So just by hovering on the different dimension, they can quickly get a sense of the relationship between multiple dimensions. So just to play this again. So just by hovering on the slider of hunter, fierce, and timid, and they can quickly figure out that the hunter and the fierce, they have the same relationship, but the timid, it has the opposite relationship with the other two. However, we think the dimension assist feature is, they just think the dimension assist feature is only a little bit helpful for data distribution, especially when there are a lot of data points overlap with each other, or the variance of the dimension value is not significant. And we also monitor the participants' interaction to discover some potential patterns. So although the functionality of the dimension assisted feature overlap with the parametric interaction on finding stream and the defining data distribution, the dimension assisted feature has a shallower learning curve than parametric interaction. And also, dimension assisted feature is more efficient and accurate than surface level interaction. And the surface level interaction, it is very easy to overlook some important data point. So overall, we think the dimension assisted feature offers some improvements on acquiring dimension related information. Okay, so the last cognitive gap is the Andromeda system cannot deal with the clustering problems. So for example, the user here want to create a cluster of German Shepherd, Otter, and Dolphin to express their similarity. And the user may expect these 3 points should create a cluster in a new visualization. However, in the original system, the model only captured the similarity relationship among points. Like here, the otter should be more similar to the German Shepherd than the Dolphin, but the system failed to capture the intention of creating a cluster. And the reason is because the system is because some relative distance is missing in the clustering task. For example, like here, when we create a cluster, we only specify the distance that should decrease, but we did not specify the distance that should increase because we did not highlight the wolf here. So the distance between these 2 points are not counted by the system. So that is the one reason. And the solution is one solution is to consider all the untouched points, which means the cluster point will move with respect to all the untouched points. However, this solution is not only computationally expensive, but also our change will minimize by lots of untouched points. So our solution is random sampling, just randomly sample 3 points to represent all untouched points. Like this video. So once the system detects a cluster-related intention, it will randomly select the 3 points. Like update now, and you see 3 points has been sampled. And in the new visualization, these 3 points has been clustered. And same for the deconstruction of cluster. Also 3 points will be sampled. Yeah. Okay. So to analyze our design, we did a simulation analysis to evaluate the random sampling. And we used 2 versions of Andromeda. Again, the version B is enabled the random sampling, where for version A, the random sampling is not enabled. And we create a cluster with 2 to 5 points. And in the graph, the green dashed line is the original distance. The olive dashed line is the user-defined distance, like the distance between the created cluster. And the blue line is the regression line for the new distance generated by the version A, where the coral color line is the regression line for the new distance generated by version B. And as we can see in the graph, the coral line is always under the original distance line, which means in general, the tested point creates a cluster in version B system. And also we can see that the coral color line are always under the blue line. And that means the system B has a better clustering performance than version A. And this graph demonstrates the result of deconstructing cluster. And from the graph, we can see the system has better performance when they have the small original distance, but poor performance when we have large original distance. And this is probably because the points with large difference is probably is already at their furthest largest position, so it cannot be separated again. And and we also test on the deconstructing cluster with 3 to 5 points. And again, you can see the regression line of the version B is higher than the version A, and this indicates that the system B has a better performance on deconstructing a cluster. So in conclusion, we identified and provide solution for 3 cognitive gaps, and they cover both black box on human-computer interaction. And among them, the highlighting relevant data points and understanding the WMDS dimensions rises because the user don't understand our models. So we developed 3 user interface features in the front end. Well, for the 3rd cognitive gap, constructing and deconstructing clusters, this happens because the model cannot capture users' clustering intentions. So we set criteria for constructing and deconstructing cluster, and we implemented the random sampling to facilitate the cluster-related task. And we conducted 2 user study and 1 simulation analysis. And all the results indicate that our solution can elevate the corresponding cognitive gaps. Yeah, so that is all the thing about my presentation. And thank you, everyone. And thank you for listening my presentation. Okay.
Thanks, Ming. That was really great. That was a great overview of solving a number of design and usability challenges. There's one question that came up in the chat that asks if you can briefly expand about the random sampling work and how does the random sampling actually address the clustering challenge by selecting 3 points?
Okay, yeah, so for the random sampling one, yeah, so actually we have, did you mean the experiment part? Or just
I think the question was more along the lines of why are we randomly sampling in order to understand the clustering motivation of the user, or to basically understand what the user's interaction is implying.
Okay, so actually in our the original system, we actually because for our system we only consider the relative distance. So when we are doing the cluster related intentions like create a cluster, we only specify the relative distance that should decrease by missing the one that should increase. Like in this example, like the distance between the wolf and the German Shepherd, this distance is actually missing in our computation. So that is why our original system cannot capture the intention of creating a cluster. So our solution is trying to help our system to capture this intention, even this is missing. So one solution is we can just consider all other untouched point, like all this blue point here. And that means our cluster is created in respect to all other untouched points. But this, as I mentioned, this solution is very computational expensive. You need to compute the relative distance between all other untouched points. So that's why we want to just sample a few points for this untouched point. Just use that few points to represent all these untouched points. And we did some analysis and find with the increasing number of the representing points, actually the performance will decrease. So it just indicates that the small number of representing point would be better. And that's why we just use 3 points to represent all these untouched points. And we consider the distance between this, between these untouched points. It's kind of like this distance we'll use as a reference. This distance between untouched points we use as reference and compare with this touched points. So by comparing them, we can kind of like do some computation on the relative distance, and that will kind of like in our results, like improve our performance. Yeah, so don't know if I answer your question.
Yes, yeah, there was a follow-up message that said that it makes total sense, and so thanks.
Awesome. Yeah, thank you.
Okay, so just for the sake of time, that's where we'll wrap up with the questions for this session. So thanks again, Ming. If you do have any more questions for Ming, then please post them up in the Discord or in the YouTube chat, and we will get them to Ming so that she can answer them in the very near future.
Awesome.
So
yeah.
now for the last 17 minutes or so of the official session, we need to make things a little bit complicated and see how messy we can make a virtual workshop. So in the chat, I'm just posting in the link to a Google spreadsheet that has links to a variety of breakout rooms so that we can do a little bit of discussion. And let me also just quickly share a screen that has that window inside of it, if I can find it. Here we go. So there are 5 different breakout rooms at the moment. Ignore the 3.2 personalization session because that's coming from session 2. In these breakout rooms, we have one of our workshop organizers who is going to be facilitating, but it's still your job overall to be able to take notes, to capture what interesting things that your group has discussed. And there are also passwords listed in this last column, and also Google Doc links that you should hopefully have edit permissions for, so that you can take notes and we can get something from our organizer side out of the workshop. If you're not interested in going to one of the breakout rooms, then feel free to stay here. I'm going to stay inside of this main room. If you have questions about the workshop, past versions of the workshop, future versions of the workshop, anything in that space, then feel free to ask them in the main channel. Otherwise, have a very productive discussion session. This set of talks already this morning has really raised a number of questions and a number of research thoughts in my mind, and I hope that it's done the same for you.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
The transport dynamics in an unsteady flow can be visualized by the finite time Lyapunov exponent. But what happens if the flow contains random Gaussian deviations? We introduce a recently published quantity that is similar to the FDLE but considers these stochastic deviations. We discuss the application to real-world data, compare it to prior methods, and present a complementary visualization.
A Morse-Mean complex is a topological descriptor that captures the gradient flow of a scalar function. The best-known approaches for its computation incur large runtimes for bigger datasets. We address this gap by introducing the first completely GPU parallel pipeline, which achieves speedups of up to 7x, with our individual algorithms attaining speedups of up to 129x and 4.5x.
How can we sample multivariate data such that we can preserve as well as utilize the variable relationships? For that, we first partition the data, and then for each partition, we perform PCA to model the variable relationships and followed by sampling to reduce the spatial resolution. We can then perform different multivariate post-hoc analysis directly on the reduced data form.
In visual multivariate analysis, we often want to find out how the variables in the set relate to a particular target variable. Imagine we have medical data from patients that suffer from a specific disease. Then we might like to understand which conditions predict a more severe progression of the disease. This is a challenging task because the explanation could involve a specific combination of several factors. We propose a novel method based on neural networks to visually explain relationships in multivariate datasets that can also recognize more complex, nonlinear correlations.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element: visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
The daily work of criminalists consists of analyzing relationships in complex data while proposing and verifying multiple hypotheses, often under heavy pressure. This poses high demands on their memory and cognitive capacity. We present Visuland, a tool that helps investigators track their visual exploration and reasoning. It organizes analytical state in a graph structure which can be revisited and shared with colleagues.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained datapath extraction method, a river-based visualization, and a contribution analysis method.
We present stratigraphics, an approach for designing data-agnostic and fully reusable visualization templates. Stratigraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variety.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
Billions of biologging records reflect animal behaviors on many temporal spatial scales, yet segmenting the time series on multiple scales is often avoided or impeded. Hence we present our MultiSeg VA platform with its 3 contributions. First, MultiSeg VA contributes tailored visual interactive features for multi-scale segmentation. Second, we show a new visual query language to flexibly configure scale-wise techniques and parameters. This VQL consumes a domain-oriented set of techniques, our third contribution.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
Carex S is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We find that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
In human brain mapping, atlases are indispensable tools to neuroimaging experts. While many of these atlases capture general trends over large populations, they fail to capture subject-specific complexity of brain organization. We proposed Pragma, a tool for interactively deriving individual-specific brain maps from established atlases. Pragma supports within and between parcel analysis to help experts make decisions during the parcellation process.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
The recent COVID epidemic has triggered several different crises that are testing our civilization's potential for both coordination and cooperation. Data about infection rates and their growth has been the main source for public discussion and has inspired many visualization works. We propose a VA approach that incorporates a growth predictive model. This allows the correlation monitoring of the virus population development. We also can relate it to different government response events, as well as identify key dates.
Forensic investigation of file system metadata is a difficult and time-consuming task that requires deep expert knowledge. Following a user-centered design, we implemented an analytical tool to guide analysts during a security incident investigation. The evaluation proved that the tool could significantly improve the efficiency of disk exploration, even for less experienced analysts.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduced the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the test to your requirements at the interactive testing section and observe them at the testing evaluation section.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift-level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
We present a method for real-time ray tracing of stream tubes for fluid flows and diffusion tensor MRI. Rays are traced through a sparse voxel lock tree until they intersect leaf nodes which contain tube segments. This checkerboard pattern indicates voxel boundaries. Within leaf nodes, we can ray trace straight tube segments or ray cast curved tube segments.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
When visualizing data in a realistic rendered 3D environment, it is important to represent the data in a readable way. In our work, we investigate how the opacity affects the readability of a 2D shape and determine useful opacity ranges. Therefore, we performed a user study with different overlay configuration like filled, striped, and dotted pattern, their density, and considered the effect of an outline.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
Druid.js is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical
All right, hello everyone, and welcome back.
So we are going to go ahead and kick off pretty quickly here our second session for our workshop, which is machine learning from user interaction. So just a really quick overview for those of us who were maybe not part of our first session here. The focus of our workshop is kind of talking about these three different components of, I'll say, a pipeline that involves machine learning, a visualization, and the user. So these set of arrows kind of represent what is commonly known as explainable AI, where you have the machine learning algorithm that then helps produce a visualization of what happened with that machine learning algorithm, and that visualization is then presented to the user. In human in the loop, which is kind of this long back arrow here, the user is somehow directly manipulating that machine learning algorithm to then update the visualization and interact with their data that way. What we're talking about here, though, with machine learning from user interaction is more this, that the user is interacting directly with that visualization to then, by extension, interact with that machine learning algorithm. So all these ideas are obviously related and have some overlap between them, and that's what we are exploring here in our workshop. So without further ado, I'm going to go ahead and kick it off to our second keynote by Olivia Ottley, who will be talking about using models and predictions to help humans and computers click. Is Olivia with us? Or Alvitta, excuse me.
I am, but it should be a pre-recorded talk.
Oh. Where? Okay, thank you.
Hi everyone, this is Ming. So in this video, I will talk about our work on bridging cognitive gaps between user and model in interactive dimension reduction. Our lab has developed a great interactive visual analytics tool called Andromeda. It relies on the WMDS, which allows users to shift emphasis on different dimensions so that they can explore data from different aspects. A lot of great work has been done to set up this pipeline.
Hello everyone, my name is Alvitta Ottley, and today I'm going to be talking about how to use models and predictions to help the human and the computer click. Over the past few years, I have spent a lot of time thinking about what can we learn from passively observing interactions. In fact, Kai, Connie, Mark, Remco, John and I published a VIS state-of-the-art report with the goal of summarizing the body of work on the analysis of user interactions and visualization provenance. We wanted to understand the trends in the visualization provenance research. Among other things, we wanted to use a bottom-up approach to identify the goals of the community, highlight the things we collectively are trying to achieve, and to understand the major roadblocks. I'm going to use the same guiding principles for this talk. I will begin with the findings of the survey, with a focus on the reasons why we analyze provenance data. Then I will highlight some of the recent and promising work from my group, the Visual Data Analysis Group at Washington University in St. Louis. And finally, I will discuss what I think are major roadblocks and future directions in the area. In this survey, we focus on the analysis of user interactions and provenance data in the field of data visualization, whose main purpose is similar to meta-analysis as defined by Reagan. As such, we only include existing work that incorporates meta-analysis based on user-generated provenance data, most of which had the high-level goal of improving, enhancing, or understanding either the visualization system, the visual analysis process, or the user herself. We started by collecting existing work that we knew from our previous research. We continued with the systematic approach by manually screening all issues from 4 journals and all proceedings from 5 conferences or symposia over the last 11 years, starting in 2009 and ending in 2019. We used a 3-staged process for tagging. To start, each author was assigned to at least one conference or journal to screen. This process resulted in a collection of 266 papers. The aim of the second round of coding was to unify the categories and narrow down the scope. Each paper was coded by at least 2 co-authors independently. We worked together to resolve cases of ambiguous or uncertain classification. In the last stage, we finalized our tags and created 3 main categories: why, what, and how, and I'll explain these in the next slide. After going through all 3 phases, we ended up with 105 papers. We created a table that shows the final tags, and they are organized under 3 high-level categories: why we analyze provenance data in green, what types of provenance data and ways to encode it in brown, and how to analyze provenance data in blue. I will refer you to the paper for all the details, but for the sake of this talk, I want to focus on why. One of the dominant reasons why researchers analyze provenance data is to understand the user. And this makes sense, because we have to first understand the user in order to evaluate systems and algorithms, inform intelligent responses, improve the underlying projections and machine learning algorithms, replicate, verify, and reapply analysis techniques, and to generate reports automatically. But because understanding the user is core to all of these reasons why we analyze provenance data, it warrants further inspection. And the primary goal of this category of research is to create theoretical and computational models that describe the reasoning process. I often find myself asking the question, what should we be learning? Now, I'm thinking moonshot. If you can wave a magic wand and know everything you want to know about a user, what would that be? Here's my moonshot heptagon. I believe that it is important to know the high-level task and how it evolves over time, the user's attention and also how that evolves as they are completing a task, cognitive biases, knowledge or expertise, abilities and personality, preferences, and the context or their situational environment. I don't know if this is complete, but the goal was to create a full picture of who a user is and what they're trying to do, and the state of the environment, independent of what we will do with it. From our survey, we saw several examples in the prior work where researchers have tried to understand the user, and there are several that demonstrate the ability to do these in real time as well. Some of the examples include quantifying hover and click patterns, predicting personality traits, uncovering exploration bias, and modeling attention. So overall, we see evidence that we can identify users' attention, biases, knowledge, and personality from their interactions. And I've been fortunate enough to be involved with some of these projects, so I'm going to spend a few minutes highlighting some of this prior work I'm going to begin with work where we demonstrated that we can learn users' personality traits based on the observations that we make with their interactions. We began this project by asking, can we infer user characteristics from mouse interactions? And this project was motivated by some of our prior work that demonstrated that individual differences, such as personality traits and cognitive abilities, can impact speed, accuracy, and strategies on visualization tasks. To investigate this, we use this following game. So this is a popular children's game and it's called Finding Waldo. The objective is to find Waldo. He is typically dressed in a red and white striped shirt and a blue pant. To search for Waldo, the participants use these control buttons. They can go up, down, left, right, zoom in or zoom out. They also pressed found when they thought that they found Waldo. So in total, there were 7 control buttons. We logged users' interactions as they searched for Waldo. In this particular illustration, Waldo was very difficult to find because he was hiding in the bushes. There were also several distractors for people who were dressed similarly in red and white striped shirts, like Wendy here. We recruited 90 online participants for the experiment. The mean completion time was about 7.8 minutes. The fastest 15% were able to complete the task within 2 minutes, and the slowest 15% completed the task in about 13.7 minutes. We captured mouse clicks and mouse moves and collected personality data. As a first step to analyzing this data, we started out by visualizing it, and you can think of this representation like a node link diagram where the nodes represent a viewport and the links represent a transition from one viewport to the other. Thicker, longer lines represents a user being really zoomed out and making transitions, and smaller, thinner lines, shorter, thinner lines means that a user was really zoomed in as they were looking for Waldo. Using this representation, we were able to aggregate different types of users. For instance, when we look at users who were quick at completing the task versus users who were slower at completing the task, we see a drastic difference in this visualization. For instance, people who were slow at completing the task were really zoomed in on the illustration and made small steps while they were looking for Waldo. On the other hand, people who were quick at completing the task were really zoomed out, and they would only zoom in once they think that they found Waldo. This strategy turned out to be more efficient overall. To analyze the data, we used a combination of 3 different types of data encodings with 2 different off-the-shelf machine learning algorithms. And this was actually pretty good at separating and classifying people based on whether or not they're going to be fast or slow. So on average, we got about 80% accuracy at this prediction task. Now, what about individual differences? There is a growing body of research on how individual differences in personality and cognitive factors might influence how people interact with visualizations. In fact, my colleague Jordan, my student, and I recently published a state-of-the-art report on this topic, and I encourage you to look at it if you believe that this might be interesting to you. Now, although there are several individual differences that can come into play here, I want to focus on locus of control. Locus of control is a personality trait that describes how in control someone feels of external events. This is a continuum. So on one end of the scale, we have internal locus of control, and these people believe that they make things happen. And on the other end of the spectrum, we have people with external locus of control, and they believe that things happen to them. It turns out that prior work in the visualization community has demonstrated that locus of control can impact speed, accuracy, the amount of insights, and search strategies, as well as preference for visualization designs. It turns out that when you look at the behavior of people with external locus of control, you see that they would operate at a very zoomed in level while they're looking for Waldo, and they were significantly slower and less likely to find Waldo as well. On the other hand, if you look at people who have internal locus of control, they were fast at finding Waldo, and they would operate at a higher zoom level and only zoom in when they think they found Waldo. We were able to detect extroversion, neuroticism, and locus of control, all at about 60% accuracy. In summary, we showed that it is possible to automatically extract information about users from their interactions. Specifically, we showed that we can classify people and determine whether or not they're going to be fast or slow. And we also showed that it is possible to automatically learn individual traits. Now, this is just the tip of the iceberg. And while there are lots of work to be done in the future, this was just an example to show what the possibilities are. I'm going to move on now to some of our more recent work, where we demonstrate that it is possible to track and predict a user's attention during analysis. And this is motivated by the realization that there's a true missed opportunity for supporting the human during analysis. We see that there are lots of capabilities from learning from interactions. For instance, prior work has shown that we can identify a user, and this is in the machine learning domain, where they showed that it is possible to authenticate a user based on their keystrokes. We also saw in the visualization community that interaction data can contain important information about analysis strategies, and as we saw in Waldo, we can predict performance and personality. To frame the problem space, let's consider the following example. So right now, you're looking at a map of St. Louis. Every dot on this map, so every circle represents a reported crime in March 2015. Each color of the crime represents a type of crime. For instance, homicides are in red, theft-related crimes are in blue, and we can see that the majority of crimes in this area are theft-related crimes, for instance. Now consider a user interacting with this map. They might zoom in to this green area here, which is Forest Park, and you might observe then that they start interacting with dots. Now a human that is looking at this interaction would then be able to recognize that maybe this person might be interested in crimes that happen in Forest Park and can predict that they're going to interact with these pink dots here that are in the park. Now the question that we posed was, can we train a machine learning algorithm to identify patterns of interaction? And the high-level goal is to leverage passive observations of interaction to model and predict actions before they occur. With this project, we present a generalizable framework for using machine learning to model the user's attention while using a visualization system. We also demonstrate how we can apply this model to a crime map visualization and show with a user study that we can apply this model to accurately predict clicks before they occur. At a high level, the work in this paper applies machine learning to time series data, and we make the following assumptions. We assume that samples arrive sequentially, and that sample sizes are unknown or might vary depending on the user or the task. We also assume that data are not available during training, and that waiting until time t to accumulate a batch may not be feasible. So these circumstances eliminate many deep learning techniques, such as RNN, which are notoriously difficult to train and require a temporal relationship of the past to be similar to that of the future. Given these assumptions, we decided to use a hidden Markov model to represent a user's evolving attention. Now, hidden Markov models work well for small data, and they work well for streaming data. Also, we don't have to wait for a big batch to make predictions about future steps. Theoretically, you can predict after only a single observation, though the accuracy of that prediction depends on how you define the prior. Now let's talk about how we can apply hidden Markov models to visualization. The hidden Markov model has 4 main components. First, we need to define what a hidden state is, and this is the space of possible interests that are driven by salient visual features. Second, we need to define what observations are, and we see this as a space of possible interactions. Third, we need to define the dynamical model, And this is a model that describes how users' attention evolves over time. And finally, we need to define the observational model. And this describes how attention might give rise to the observations that we see. For most visualizations, these can be fairly straightforward to define. Let's begin with the hidden states. Recall that we are trying to model attention. And what do we mean by attention? Well, basically, people attend to what they can see. So to build the hidden states, we decompose the visualization into its low-level visual marks and channels to create feature combinations. We use these visual features to define our mark space, which is a set of n visual features extracted from the visualization, for example, position, size, and color. For the observational model, we define this as any interaction with visual elements, and this could be mouse click, keystroke, eye gaze, speech, pan, zoom. This really depends on the visualization design, and we try to define this as general as possible. Now let's look at the dynamical model. Recall that this describes how a user's attention shifts over time. And we assume that z sub t is the latent attention at time t. We also assume that an analyst's attention evolves slowly, which means that attention at time t plus 1 is similar to attention at time t, where epsilon is some appropriate noise distribution. However, this only works for a single task, but in the paper, we provide lots of details about how this might work with multiple tasks, as well as different types of features, for example, continuous, categorical, or ordinal. Now finally, how might states give rise to actions? The way we define this loosely translates to people will interact with elements related to their hidden attention space. In addition to these 4 components, we added one more, and this was a bias vector. It is useful to consider bias when modeling attention. We adopted the bias vector pi to capture the relative importance of various components of the mark space. In other words, we want to keep track of the features that are capturing the user's attention. Now we've all heard the saying that all models are wrong, but some are useful. And in order to test our model, we decided to run a user study. We recruited 30 participants via Amazon Mechanical Turk, 17 of which were women, and the average age was 33. For the visualization, we used the crime map as shown before. Users interacted with this map by clicking on the points, and clicking on the points revealed a tooltip that contained the type of crime as well as the time and date that crime was reported. There were 3 types of tasks in the study: a type-based, geo-based, and a mixed task. With the type-based task, participants interacted with the same types of crimes across the entire map. For example, find the homicide that differs from the others. With the geo-based task, participants interacted with different types of crimes that are constrained to a specific geographical region. For example, what is the ratio of crimes that happened in the morning in the red shaded region? Finally, we had the mixed type task, where participants interacted with the same types of crime, but were constrained to a specific geographical region. For example, what is the ratio of theft crimes in the red shaded region? We had a within-subject experiment design, and from 30 participants, we got a total of 180 trials. Now we know that Mechanical Turk data is notoriously noisy and messy, so we had to clean the data by removing participants with less than 5 interactions or who did not follow instructions. After cleaning, 78 trials remained. Although for the rest of this presentation, I'm only going to focus on these 78 trials, I think that it is important to test our models even on noisy data and data where people may not have interacted with the visualization the way we expected them to. So in our paper, in the appendix, we have included the results for all 180 trials. I have told you how we can apply hidden Markov model to visualizations, albeit at a very high level, but I never really told you how to make predictions. To do this, we use particle filtering, and this is a visual representation of this space. Here, there are 1,000 particles, and they represent the model's belief at any given time. What you're looking at right now is time t equals 0. So this is before we have observed any kind of interactions. You might notice that most of the particles are blue. This is because we randomly sampled from the distribution on the crime map, and theft crimes, colored in blue, are the most common crimes. Location was randomly sampled from a Gaussian distribution. You might also notice that there are some points that don't have a color, and this is where our bias vector comes in. Circles without a color means that we are very certain about their location, but we are uncertain about their color. On the other hand, circles with dark color, dark hues, means that we are very certain about the type of crime that the user might be interested in, but we are uncertain about the location of the crime. As a user clicks, we update our belief. The square represents the location and color of a click. This is an example of one of the user study participants that we had for the study. So how do we predict? Essentially, every particle then vote for the actual points on the map. Let's take a closer look at these particles. After observing a series of interactions with red points, we can observe that most of our particles are red, and this represents our belief about what a user is paying attention to. Again, each particle gets to vote for points on the map, both points that are of the same color and points that are in their vicinity, depending on that bias vector. Here we highlight the top 100 points with the highest votes, scaled by their probability mass. So a bigger radius means a higher likelihood of being clicked in the next time step. 100 points represents 5% of our dataset, and we consider a prediction successful if the next click falls within this prediction set. Now, even though in this talk I'm only going to be considering a prediction set of 100, in the paper we include prediction set of 50, 20, 10, 5, and even 1. So to calculate our accuracy, we look at the total number of successful predictions over the total number of predictions. Here are the results for a prediction set of size 100. On the x-axis, we have the 3 different types of tasks: type-based, mixed, and geo-based. On the y-axis, we have accuracy, calculated by the number of successful predictions over the total number of predictions made. We gave our model a 3-click period to learn, which means that we started recording accuracy after the 4th click. We can see that overall, the model performs really well across all tasks with an average accuracy of about 95%. Now let's look at how it performs over time. On the x-axis, we have the number of observed clicks starting from time equal 4. On the y-axis, we have accuracy. Each line represents the different types of tasks that were in the study. After learning from the first 3 clicks, we can observe that the algorithm, especially for type-based and geo-based tasks, it immediately achieves high prediction accuracy. We also found that accuracy remained constant over time. Now, this is a slightly different case for the mixed type task, and I think this is because the algorithm was somewhat confused with the bias vector as to whether or not someone was more interested in the location of the crime or the color of the nodes. Now, in summary, in this project, we introduced a framework for modeling latent attention. We illustrate how to apply this model to a crime map, and we demonstrate that this model can accurately predict interactions before they occur. Similar to the Waldo project, there is still a lot of work to be done. We demonstrated that we can model attention with a single crime map and a highly specified set of tasks. We need to be able to do this across lots of different visualization types and across both goal-directed and open-ended tasks. The next project that I want to highlight sought to model and track both users' attention and biases during interaction. This is going to be a little short overview because this paper will also be presented later this week in the Intelligent Systems track on Thursday. The motivation for this project is the acknowledgement of the limitations of the prior work, and this is true both in the case of the projects that I've contributed to and the other existing work in the community. This is not necessarily a flaw in the community, but it exists because there is just not enough work in this area, and we're still in our infancy in terms of developing useful user models. So researchers have proposed multiple techniques to modeling user interactions. However, their frameworks often depend on the visualization design, interaction space, and dataset. And again, this makes sense because we have to start somewhere. Additionally, we haven't compared these techniques on equal footing, so it is difficult to know which to apply and when they are most helpful. But perhaps we can think of these user models as tools in our toolbox. And then the question becomes, which tool should I use right now to help the user? I know that I'm jumping a bit ahead because we haven't really talked about how to use these tools, but choosing the tool is important. And that's where this project comes in. In this paper, we propose using Bayesian model selection to maintain a belief over numerous competing models that can explain user interactions. Each of these competing models represent an exploration strategy the user could adopt during a session. The goal of our technique is to make high-level and in-depth inferences about the user by observing low-level interactions. Although our proposed idea is applicable to various probabilistic model spaces, we demonstrate a specific instance of encoding exploration patterns as competing models which are defined based on the features in the dataset. We validate our technique's ability to predict feature interactions, infer exploration bias, and summarize an analytic session using existing user study datasets. The results are very compelling, and in the paper, we discuss how practitioners might use the proposed paradigm to choose the right modeling tool from their toolbox when building intelligent visualization systems. Again, I encourage you to visit our talk. It's going to be in the Thursday session under intelligent systems. The final project that I want to touch on seeks to understand users' knowledge based on their interactions. The goal of this project is to learn about users' knowledge of the task and data and use this information to power active search queries and suggest data items in real time. Consider the following scenario. The data is being visualized, and the user interacts with the data through visual queries and whatever interaction modalities that are afforded by the design. We assume that we can model the underlying relationships in the data, and similar to prior work on model steering, we learn these data labels in real time by observing user interactions. We then use these labels to power an active search paradigm that then allows us to update the visualization with suggestions that we believe might be relevant to the user's task. We evaluate the utility of this approach with a user study. We use the fictitious epidemic dataset published by the VIS challenge. The task was to search through social media posts to identify symptoms and the impacted parts of the city. There were two groups in the study, a control group and an adaptive group. The task was an information foraging task. Each person had a maximum of 10 minutes to find and bookmark tweets that contained information about how the epidemic is being spread. Our results suggest that we can indeed represent the user's knowledge of the data and use this information to power active search algorithms. When compared to the control group, our adaptive group was more likely to interact with points that were relevant to the task. Adaptive groups also forwarded significantly more tweets per minute. Perhaps one of the most interesting findings of this study didn't really have to do with the adaptive system at all, or whether or not we could represent a user's knowledge. But I think that this finding is a good segue to discuss some of the things that I believe are important for future work. When you take a closer look at participants in the adaptive group, we noticed a bimodal distribution for recommendation usage. So here on the x-axis, we have recommendation usage as a percentage, and on the y-axis, we have the count. So this is a histogram. As you can see, a non-trivial portion of participants in this group largely ignored the suggestions. And from the post-survey, we saw that people in that group said that they did not trust the system. This finding has important implications for how we might utilize user models in the future. Looking back now at our moonshot heptagon, we have clearly made progress in understanding the user. But this slide is misleading because we're just getting started and there is still a lot that we need to know. For instance, we need to dismantle the notion that when someone sits in front of the computer, they stop being a person. There is still a lot that we don't know about how individual differences impact visualization use. And although we have taxonomies, we lack theories of task definitions, granularity, and complexity. The existing taxonomies are largely descriptive but not prescriptive. Finally, I think we need to move beyond mouse and keyboard interactions and start thinking about different modalities for interactions and how a user's situational environment might impact the way they use visualization tools. But let's not lose sight of what we have accomplished, even if we're not that close to the moon. We have techniques for modeling attention, biases, knowledge, and I believe that modeling personality is very much possible. The field is mature enough for us to start aiming to apply some of these techniques on real-world applications. Let's look back at the findings of the state-of-the-art report because it revealed some promising applications for user modeling. We found that one of the fastest growing area was adaptive systems, and with the rebirth of AI and the prevalence of adaptive tools in the home and on smartphones, this can mean exciting and new opportunities for visualization research and visualizations in practice. We saw several examples of adaptive system with the aim to improve the usability and performance of a visualization system. Topics range from recommenders, providing guidance to the user, and adaptive prefetching. I think that we can do so much more, even with the limited models that we have. But we need to think about the user's preference and perception of such systems, and we also need to actively address issues of trust and explainability. With that, I want to give a huge thank you to the students in my lab who are spearheading this work, and also to the collaborators on these projects and the funding agencies that supported this work. I also want to thank you for listening, and now I'm happy to answer any questions.
Thank you very much, Alvitta. Excuse me again. Thank you very much for that wonderful presentation. I found it personally to be quite fascinating. And so if anyone has any questions, please feel free to put those in the chat, either in Discord or on YouTube. And with that, I guess let's jump into some Q&A. So to get us going, I was really curious when you mentioned that initial 180 trials. Can you maybe highlight what are some of the findings, especially how they differ from your clean data set when you did that evaluation?
Yeah, well, first, thanks for having me. I'm really happy to be here, and thanks for the invitation. So overall, we saw this similar trend, but just the accuracy was a little bit lower. So, I mean, with the clean data set, like we got an average accuracy of about 95%, which is very high. But once we look at the more noisy data set, it dropped down to about 80-something%, which is still very good.
Yeah. Cool. Yeah, I mean, it seems to me like that's an expected result from an experiment like that. I guess jumping into another question here, you mentioned that the bias vector that you used when you were doing your experiment with attention maybe led to the algorithm being a little bit confused. Can you maybe speculate on how the algorithm can maybe be updated to reduce that confusion?
Yeah, so I think that kind of stemmed to the assumption that we made. And the assumption is that for a given set of visual features on a visualization, we're kind of assuming that you're either on one end of the spectrum where you're paying most attention to one thing, or on the other end of the spectrum where you care more about the other thing. And the setup doesn't really facilitate that. You might be interested in both things at the same time. And that was just a flaw in how we set up that vector. And I think instead of having it as a single vector, a single value that range from 0 to 1, we can do almost like a model selection approach where we consider interests that is at the intersection of all combinations of features. So that was just a flaw in our experiment design. Well, not really, but the way we set up with models. But I think the beauty about that technique and the hidden Markov model, that is completely customizable. And so it's really easy to change that specification based on the visualization encoding, based on the task. I think that there's just a lot of flexibility with it.
Yeah, cool, very cool. So question from the chat, what do you expect the accuracy will be like once the task becomes more open-ended? Like in the crime map study?
I do have an answer to that question because we, in the Bayesian model selection paper that we did, that's going to be presented by Cheyenne, who's a PhD student in my lab. He's going to be presenting it this Thursday. But in that, we did a comparison where we compared the Bayesian model selection to their hidden Markov model approach. And of course, it's going to be more noisy. It turns out, though, that it's feasible to predict because people actually perform in very predictable manners. And that really means that if someone is interacting within a certain area, they are very likely to continue interacting in that specific area. So I'm even like to be completely honest, I feel like if you, and we've tried this, if you model it with even like a simple KNN, it's a KNN in a lot of times can be sufficient at modeling simple tasks when people are just doing open exploration, because I think we're just very predictable.
Cool. Well, I think that's it for questions at the moment. So I want to thank you so much again for that wonderful presentation. And I guess from there, we will transition into late-breaking work. So this will be a series of just short talks about some more recent work or work in progress from a number of people. And it looks like we have 5 different presentations. So let's start with our first one here, which is from Bilikis Banir, I'm sorry. I hope I'm not butchering your name. And his talk is titled Gaze-Based Attention Recognition Model for Children with Autism Spectrum Disorders.
Thank you for having me. Hello, can you hear me?
We can hear you, but you're very quiet.
Okay. Is it better now?
No, you still sound quiet. We can hear you though. We can hear you.
Okay. Thank you for having me. Okay. My name is Bilkis Banire. I'm from Ahmad bin Khalifa University, Qatar. Today I'll be sharing with you our research, which is titled Gaze-Based Attention Recognition Model for Children with Autism Spectrum Disorder. This is under the supervision of Dr. Dina Athani and Dr. Marwa Farki. Just to give you a quick introduction about who children with autism are, they are characterized with neurodevelopmental disorders, and they exhibit social communication deficits and atypical attention. So it is difficult for one to identify when they pay attention and when they don't pay attention, especially when you give them a task to do and they're actually looking at it. You cannot tell if their mind is on it or they're not paying attention. So it is quite difficult. So the intention of this research is to find a way to automate how they pay attention and when they are not paying attention. And to do this, we design an attention task, which is based on continuous performance task. And this is conventionally used to measure sustained attention. And in this case, we simulate a real class scenario where we have distractions in the classrooms and we have the target stimuli on the board. So they're expected to look at the board and click when a target letter appears. And once that is done, that is considered as attention. And when they miss the target letter, that is inattention. So at each time frame, we label this recorded video using, we use this screen-based eye tracking device to track their eye movements while they were doing the task. So this is just the scenario of the experiment whereby we have the participants seated in front of the system. And while they are taking the test, we try to highlight this frame at which they click correctly and when they don't click correctly. So we use this screen-based eye tracking device to monitor their eye movements while they take the task attention. So we look into the content-based features such as fixation duration, where they are looking at on the stimuli. Are they looking at the target stimuli or they are looking at other distractions in the classroom? We also looked at non-content based, such as the pupil size and the ocular distance to the screen. After that, we did some feature selection to identify the relevant feature that can improve our machine learning algorithm. And we tried it with several classifiers, but SVM had higher performance. And we used that to predict attention and inattention. So based on our features selection, the total features we use are 12 in numbers, like we have the content-based and the non-content-based. And the best features we were able to achieve, to come up with were pupil size of the left eye, the distance, the distance of the left eye to the screen, the fixation duration where they are looking at on the stimuli, and then the fixation point. So based on these features, we trained participant-dependent model, which is whereby we have the trained data set and the test data set on each participant, and we have the average for all participants. Sorry, in total we have like 20 participants, but we had to remove 7. So in this particular one where we have 13 participants, the accuracy was 0.985. Another model we tried was participant independent, which is generalized. In this case, we trained like 12 participants and test on the 13 participants. So with that, we found the average, and comparing the two models, we saw that the participant dependent has higher performance, which shows that there's a variation in how they pay attention in terms of the features we have looked at. That about the research, and thank you very much for listening. I would like to welcome your questions and feedback and your contributions to our research. Thank you very much for having me.
Yeah, thank you very much. So anyone who has questions, feel free to post them in the chat. We're going to do all of our late-breaking work presenters and then have a collective Q&A for all of our presenters for this portion of our workshop. So again, please feel free to post them in the chat. And without further ado, let's move on to our next presenter, Yali Bian, whose talk is titled Visual Analytics with Deep Learning and Semantic Interaction.
Hey, can you hear me and see the screen? Okay,
yes,
perfect.
Yes, you're good.
Yeah. Okay, so hi everyone. My name is Yali Bian, and from Virginia Tech, works with Dr. Chris Noss. And in our research topic, visual analytics with deep learning and semantic interaction. So first, semantic interaction is a methodology for visual analytics to capture users' preference or mental model about the dataset based on their interactions during the sense-making loop. So by learning a new distance function based on the input features. So this means the inference ability of the semantic interaction model is highly dependent on the quality of the input data features. So deep learning is the state-of-the-art representation learning methods that can automatically learn high-quality features for the input data. So this means it provides a good opportunity to improve the inference abilities of semantic instinct models. So so by this we mean so far as those are high-level abstract but meaningful DR representations could capture users' mental models like accurately. So far we explored two ways in using deep learning models in our semantic indexing pipeline. So first is the straightforward solution is we're using deep learning models as the fixed feature extractor. This means those DR models could provide the fixed, the pre-trained, and the general purpose representations and to capture users' mental model. So, and a further design for this is instead of using this general purpose representations, how could we get the contextualized deep learning representations, based on users' interactions to get to improve the inference ability. So this way, we find a solution to integrate the interactive deep learning training based on semantic access and integrate it into the semantic access pipeline. So for the first prototype, we have the semantic access models with the pre-trained CNN representations in capturing the user's defined visual concept. Here is the antlers. So it's like the deers with antlers or without antlers. So for the second prototype, we have the semantic access models to train the BERT model inactively to get a fine-tuned BERT models which can provide much more user and task-specific representations to capture the user's predefined concepts. Here is the risk factors about the COVID-19 research articles. Yeah. So yeah, that's all. And if you have any questions, so feel free to ask and think after this series of the talk.
All right, thank you very much. Our next presenter is Sunwoo Ha, whose talk is titled Uncovering User Interest During Data Exploration via Unsupervised Clustering.
Hi. Can you see my screen?
Yes, we can.
Okay, cool. Hi, I'm a second-year PhD student at Washington University under Dr. Ottley, who just presented. So my most recent work was on uncovering user interest during data exploration via unsupervised clustering. Sorry, my slide is not working. So the main motivation behind our project was because the emergence and increasing usage of large and dense data sets pose a challenge to both the user and visualization designers. And as the visualization becomes more congested with information, it grows difficult for the user to make observations because of information overload. And one of the solutions that have gained a lot of interest in recent years is to create intelligent systems that learn the user's interests and aid in data exploration. But inferring high-level interest is still an open challenge. So in our paper, we proposed a user interaction modeling technique with a generic two-step approach. And the first step involves a pre-processing phase that applies k-means to uncover natural groupings and patterns in a data set. And we use the output of the algorithm to create data models that are organized by their characteristic set. And in the second step, it becomes a simple lookup task as we observe the user's interactions. And given the set of interactions, we actively select a characteristic set that best explains the pattern of interactions that we observe for a given user. And we focus on clicks as a sole indicator of interest, but our method can be expanded to include data points from other means of interaction, such as hovers, zooms, and etc. I won't go too much into this, but we validated our technique with to discover user interest with Professor Ottley's Follow the Clicks user study. And this slide just shows that we were able to predict the ground truth task with our technique. And so this technique could be incorporated to an adaptive visualization system that supports users during data exploration by providing filter recommendations in real time using the model's predicted interests. So let's say, given this map of St. Louis, a user is thinking about the location of her restaurant, is concerned about the crimes that occur in the city, and then she notices that there are a lot of points on the map and is a little overwhelmed by the data shown, and she starts interacting with theft-related crimes because it seems to be the most commonly occurred crime. And after interacting with a couple of theft-related points, she gets a suggestion from the system which detected her interest in theft-related crimes. And she proceeds to take the suggestion from the system and filter out other types of crimes to explore only theft-related crimes. And so now she's able to compare these crimes across different neighborhoods and continues her search. And she's heard that like districts 2 and 5 have advantages for businesses such as restaurants. So she starts looking at theft-related crimes across those locations. And so now the system is able to infer that she's interested in those 2 districts based on her interactions and give insights on these districts. So yeah, this is, our next step is basically to do a user study to see how effective this framework will be in providing suggestions to the user based on their tasks. Thank you.
Thank you. Our next presenter for late breaking work is Shayan Monadjemi. And that talk is titled Active Visual Analytics, Assisted Data Discovery and Interactive Visualizations via Active Search.
Thank you, Michelle, for the introductions. Hi, everybody. Today, I'll be presenting my late-breaking work on active visual analytics. So let's make sure that my screen can be shared. Can everybody see my screen?
Yes, we can see your screen.
Perfect. Okay. This is a work I recently did with my colleagues Kwan and Henry and my advisors, Professors Roman Garnett and Alvitta Ottley. So in the optimal foraging theory, we have this idea that animals want to get the maximum food intaking with minimal effort, just like these cute dogs. We extend this theory to the information foraging theory, and that says that humans want to take as much information as possible with minimal effort. So now this is one side of the story. On the other side, there is something called active search in the AI and machine learning community. And that's the area of that's the problem of finding as many members of a rare class as possible under a limited querying budget. So like in this picture, for example, like we have a ton of data points and only a little subset of them is interesting. So this is active search. So in this project, I'm trying to combine the two to see how we can help users in data foraging through active search. So Professor Ottley went through this in her presentation. I will just very briefly cruise through it. So we have a data set. In the classic setting, we visualize it and the users interact with that data, search for what they are interested in. Now, when we add active search, so before adding active search first, what we want to do is to build model on interrelationships in that data set. And as the user interacts with the system, we interactively learn the labels. So we kind of like learn what points might be interesting to the user. Now with active search, we also can query the user and ask them to explore certain data points in order to maximize their utility, which is the final number of data points discovered. So long story short, we did a user study on a fictitious data set. This is actually a vast challenge data set from 2011, I believe. It's a fake pandemic that is going on, an epidemic that is going on, and some people are sick. These are like Twitter data. People are sick, and some people are just like wishing happy birthday to each other. And the task was for the users to search through and bookmark the ones that are related to sickness. So maybe kind of like an intelligence analysis type of task. And our results indicated that people who had active search built into the system, so people who got visual clues on what things might be interesting to them, did fewer total number of hovers, but they made more discoveries and they had more hovers on relevant data points. And by relevant, I mean data points that are related to sickness. So in a sense, our final results indicated that active VA users had more information intake with less effort. So active search in a visualization could help with that information foraging. So the later breaking work to this late breaking work would be to not only use bookmarks to learn those labels, but maybe look at more subtle things like the time they spend on a user spends on a dot to learn those labels. That's one side of the story. On the other side, how can we present those active search queries to the user? And this has to do with intrusiveness, trust, and all those topics. These are all open questions. That's all. Thank you all for listening, and I'll be happy to answer any questions in the end.
All right, thank you very much. We have one final presentation by Subhajit Das, whose talk is titled Conflicts in Interactive Objective Functions.
Thanks, Michelle. Hi, I'm Subhajit Das, a final year PhD student at Visual Analytics Lab at Georgia Tech under Dr. Alexander. I'm researching on topics related to human-centered machine learning. Specifically, I'm looking at how users can interactively specify preferences or their data analytics goals to machine learning modeling pipelines. My goal here is to help users interactively select and construct machine learning models using interactive visual interfaces. In one of our recent works, we have built a visual interface to empower users interactively create objective functions. So in machine learning, objective functions drive all models. For any modeling problem, there's always an objective function, also called loss functions, that is designed to solve for a specified goal. But usually these functions are created by data scientists or machine learning practitioners. Less experienced people or novices in machine learning are still cannot create objective functions to adjust models' performance, adhere to their goals. So using the tool that we built, users can now build objective functions using a graphical user interface to build classifiers on tabular data. These objective functions are multi-objective in nature, meaning more than one objectives are linearly weighted together to account for user preferences, with the goal to find an optimal model for the analytic task. However, these interactive objective functions can include objectives that have conflicting goals and specifications, and that is where the problem is. So these conflicts, if not communicated to users, can confuse the system as they solve to find better performing models. Thus, my current work looks at approaches to help users automatically detect and resolve some of these conflicts in interactive objective functions using a visual interface. These conflicts can be based on class labels, similarity between data samples, specifications regarding outliers, noise, or other erroneous data samples. Furthermore, this tool allows users to interactively create many variants of objective functions to compare trade-offs across objectives in relation to the model's performance. So as this is a late-breaking work, we just finished a qualitative and quantitative online user study with 14 participants, and we are very excited to share our results soon. So that's pretty much what I have. Thanks, and I appreciate for the opportunity to share our work with you all.
All right, thank you very much. Like I said, those of you who have questions, please feel free to post those into the chat. We are now going to go into a collective Q&A for all of our presenters for late breaking work. So first and foremost, there was a little bit of a technical issue with Bilkis's slides. So if she would like to come back and share a particular slide or two, perhaps in her slide deck, to show those to us and give us more context for her late breaking work, I'll give her a couple minutes to provide that as an opportunity here.
Thank you. Can you see my screen? No?
Yes, we can see your screen now.
I'm sorry. So just 1 minute. I've introduced who children with autism are. This is just the process that we performed. We did when we were carrying out the experiment. We have the participants standing in front of the attention task, and we have our eye tracking to detect their eye movements while they are taking their attention task. And we have we look at the content-based and the non-content-based, whereby we did some feature selection as well, where we fit it into SVM. We have to predict attention and inattention. So these are the 12 features that we looked at where we're monitoring the eye gaze. And the best features that we identify were the pupil size, the distance, the ocular distance to the screen, the fixation duration, and the fixation position. So the participant dependent outperformed the generalized one, which shows that there's variation in how they pay attention. That is that I just want to add to my speech. Sorry for the technical issue. Thank you very much for giving me the opportunity once more, Dr. Michelle. Thank you.
Yes, of course. It's necessary in these odd times, in this odd format, to provide opportunities like that. So apologies for you experiencing those technical issues. And without further ado, we can transition to some of our Q&A. So the first questions that we got were for Yali. And the first question for you is, was the training sample an issue, like to collect and label enough samples for training the deep learning model?
Hey, thanks. That's a really good question. It's actually in our paper, there are 2 research questions we're trying to solve. So for the first question was the training sample an issue? So the training sample is actually from their analyst or the user, which they having some preference about about the layout of their scatter plot. So they were trying to drag in some samples like to express their concept of their preference. So we tested it and applied it to a bigger data set, which found the training sample is even with a really small number of interactions, like 10 or 12, that's enough to capture the concept without overfitting to based on the noise. And also we tested it based on random sampling techniques and see how about we picking random samples from the big data set and using those randomly picked samples to training the model. And like against those really small numbers, and we see if the concept picked based on the random sampling algorithm still captured by the algorithm. So which is the result is pretty good. So for the training samples. So for the second question is the similarity was the training I think it's the time complexity for their training. So we tested on the bird model, which like in real time users will perform like a small number of interactions, like let's see 12 like labels, and we pass them into the bird model based on their semantics in labels and training this actually spend a really fast time. It's like but most of the time spent is when we're trying to transfer those high dimension representations to the 2 dimension using the MDS model. That's the part consumes a lot. So, but if we see on the screen we have 200 labels or 200 samples, it's still in real time to protecting high dimensional features like 768 dimensions to the 2 dimensions. So so that's why we are seeing the interaction is like happen in real time for the interactive bird model training. At least for bird model, it could be trained like in real time. Yeah. Hope it just answers the question.
Thank you very much. Yeah. The next question is for Subhajit. And your question is, how do you think you can increase the trust for novice users when dealing with objective functions? All right, Subhaji might have had to leave. He mentioned in the Zoom chat having potential battery issues. Subhaji, if you are still here, if you can still hear us, then feel free to perhaps text your answer in the chat, either in the Zoom chat and I will read it aloud, or in the YouTube or Discord chat. So then moving on, the last question that we got was for Sunwoo. And the question is, someone was wondering if you have considered the banner blindness problems that often accompanies recommender agents like the one you demonstrated. Suggestions can sometimes occur at inopportune and unexpected times during interaction, and this is jarring to the experience. So I guess the overarching question is if you have considered the banner blindness problem.
Yeah, so I feel like this is a well-known problem. Even with like previous papers that I've read, like some users are unwilling to trust the system in terms of like their suggestions. And so what I wanted to do was just, let me share my dashboard, I guess. Share. So here, it's not, I don't think it would be too jarring because it's just a pop-up at the side and they could ignore it if they do think that it's disruptive. But yeah, we have thought about like different ways that we could give notification to the user that something that they might be interested in, but something like a pop-up would definitely be, I think, somewhat annoying to some users. Maybe like a little notification here, but also that could be more jarring, I guess, than just a simple pop-up that comes off to the side. But yeah, that's still like a work in progress, and it would be interesting to do actual user studies on different ways that we can provide suggestions to users and see what is most effective. What is the most effective visual way to show suggestions? But yeah, thank you for your question.
Looks like we have a very short follow-up question. This will have to be the last question. Why not a chat box of sorts?
Oh, so like kind of like a chat box by the back end, I guess. Is that what you mean?
I'm not sure.
I mean, that is one way that I'm thinking about for another different type of project where I want to create like an AI system to help the user. But yeah, that is definitely another way that we could go about it. There's a lot of different ways.
All right, fantastic. Well, thank you all very much, all of our wonderful late-breaking work here. And from there, we are going to transition into a very brief second session for discussions. And so let me share my screen here again, just briefly. All right, hopefully you can see my screen here. So our discussion topics have shifted just a little bit, but if you take a look, here is that link again for the discussion rooms. So please go in, select which discussion room you would like to join, and yeah, feel free to talk about it. The intention is to have us all come back very briefly. So in 11 minutes, let's perhaps come back to this main room. And we can hopefully just round robin. So each of us organizers will be in one of those rooms and we can round robin between us organizers to just discuss very briefly what's been going on in some of these discussion rooms. So again, feel free to take a look at this link here. If I can highlight it instead of move the box. There we go, that one. And yeah, I will see you guys in 10 minutes. Thank you very much. Okay. So hopefully we're all kind of coming back now from our discussions. That was unfortunately short, but we do have a 1:30 end time for our workshop here. So I just want to make sure that we all have an opportunity to hear what happened in these different discussion groups. So Eli Brown, you were in our first discussion group on interactive viz of machine learning data and semantic interaction. Can you give us just a quick, maybe like 30-second overview, what was talked about there? If Eli is with us. Perhaps instead then, it's going to be easiest if I read these notes here. So let me just get into what happened. So it looks like there was some discussion about model comparison and how to evaluate systems based on user goals if user goals involve evaluation that confuses things. How to build trust, especially when the results are built off of provenance that users don't understand. And how does empirical proof of model superiority translate to trust? And trust being kind of a black box of sorts. So Eli, if you have other things to add to that summary there, please go ahead and put that in the chat. For sake of time, I will move on to the next one. And so this next group was headed by Kai Zhu. And so Kai, similar kind of thing, if you have things to add to my overview here, or I am attempting to find our notes. Okay, it looks like we don't have notes yet for group 2. For the first session in group 3, I was heading that one. For the second session, it was John. And so we talked very briefly about making visualizations obvious because, or making it obvious based on users working extensively with the data set and providing input about their knowledge of the data structure, involving them in that process so that the resulting visualization is obvious. But then even at that, if there's any variance in there, especially if it's unexplained or not very well understood variance, how do you help the users understand that better? And then how do you account for personality traits of the users, their cognitive states, cognitive traits, and bias, and things along those lines? So that was in the first part of the session there. In the second part of the session, it was about trying to talk about collaborative and competitive settings. How can algorithms detect group and changes over time, and modeling the individual versus the group, or both. Okay, and so that was for personalization. Now getting into explainable AI. There was some talk about explainability to who. So who is the focal point there? Who are you explaining things to? and what are the user's expectations. And so kind of trying to perhaps define that context for explainability, and providing an orientation to the data. Looks like trust was also discussed in there briefly. And how do users even interpret uncertainty in the first place? All right, and then last but not least, user in the loop, machine learning for user interaction. So talking about customization based on user interruption, perhaps. I'm not sure if I'm interpreting these notes here properly, excuse me. Again, please, those of you who are part of these different groups, feel free to populate the chat with interesting thoughts and insights from your group, just to help other people understand what are some of the things that you talked about. So should a user properly evaluate the solutions that are presented by the system? Trying to not bother the user too much with questions so that you're not overloading them or annoying them. So there's a need for a lightweight solution to provide feedback from the user. There's also a difference between interruptions versus recommendations, and where you draw that line, and where the user draws that line. Measuring the knowledge of the user in the loop is very important, especially when you're talking about like novices versus experts. The cost and frequency of recommendations, so there needs to be, again, some kind of metric there. And it looks like here in the notes, there are lots of wonderful examples. So I will share this slide here again with you all. I apologize for being just a few minutes over time here. So here again is that link to the discussion rooms. I know that it's in the chat, so feel free to take a look at that and explore some of these other like discussion documents from the other groups. Feel free to continue populating the chat in Discord throughout the week and continue these conversations offline. And just to close, we want to thank you all so much for your contributions and for your participation in our workshop. Thank you for attending. Please be sure to give us feedback. We want to know how well we did, especially in the context of such a bizarre year for the VIS conference as a whole. So here's that link to some feedback. And there's also some questions in there on whether or not you would like to contribute and help with our workshop either this year in writing a report, or if you would like to help us in future iterations, hopefully, of this workshop. So thank you all so much again, and I hope you all enjoy the rest of the conference.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
The transport dynamics in an unsteady flow can be visualized by the finite-time Lyapunov exponent. But what happens if the flow contains random Gaussian deviations? We introduce a recently published quantity that is similar to the FTLE but considers these stochastic deviations. We discuss the application to real-world data, compare it to prior methods, and present a complementary visualization.
A Morse-mean complex is a topological
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
How can we sample multivariate data such that we can preserve as well as utilize the variable relationships? For that, we first partition the data, and then for each partition, we perform PCA to model the variable relationships and followed by sampling to reduce the spatial resolution. We can then perform different multivariate post-hoc analysis directly on the reduced data form.